Typically, only two coordinates are needed for us to form a vector equation of a line. Here we can see it's only made of points A and B. When it comes to planes, however, which are a flat surface, there are infinitely many combinations of planes that can contain these 2 points A and B. Therefore, 3 coordinates gives us the sufficient information needed to connect these coordinates to form 2 line vectors that can lie on the same plane. So to find the vector equation of a plane, we will need to find the vectors connecting these coordinates. In this diagram, we can see that it's vectors A, B, and AC. Looking at the vector equation of a plane, we can see it resembles the one for a line, except it contains another direction vector that completes the information needed. Hence, we will need one position vector A and 2 other direction vectors B and C, which can be multiplied by constants lambda and mu, like with the typical vector equation of a line. When we draw out these 2 vectors on a plane, there is also something interesting we can do. See this vector protruding from the plane? This vector is the normal vector, which is a vector that's perpendicular to the plane, and hence sits at a 90-degree angle from any vector on the plane. To find the normal vector, we can cross product the 2 vectors lying on the plane, which will give us a vector perpendicular to both vectors. The cross product formula for vectors is given in the data booklet, but as a refresher, here is how we can cross product. For each row coordinate, simply ignore the corresponding row of coordinates and cross-multiply the coordinates for A and B for the other 2 rows. Remember that the signs must be flipped in the second row. This will give us this formula for the cross product. So, what is the significance of this normal vector? Well, once we find the coordinates of the normal using cross product, we can use it to form the Cartesian equation of a plane, which is similar to the Cartesian equation of a line, where variables x, y, and z representing any coordinate on the plane or line are incorporated. This will allow us to easily verify what points lie on the plane without having to solve simultaneously for lambda and mu, like with the vector equation. To do this, the multiples in front of the unknown coordinates x, y, and z will be the corresponding coordinates of the normal. This will be equated to d, which is a dot product of the normal vector with any position vector, which will always yield the result d. As practice, let's go through a question together. Here, we're given the coordinates of 3 points A, B, and C. We can sketch this out to give a better understanding. To find the Cartesian equation of the plane, we must first find the vectors A, B, and AC, which we can do by subtracting coordinates of B or C from A respectively. Now that we have A, B, and AC, we can cross product these 2 vectors to find the normal vector that's perpendicular to the plane. This ultimately simplifies the coordinates 1, -1, and 2. Then using this normal, we can dot product with the coordinate A to give us the value of d. Hence, the Cartesian equation of this plane will be x minus y plus 2z equals to 2, where the coefficients in front of x, y, and z correspond to the coordinates of the normal.